Hi everyone, Mrs. Basega here, and today we're working on the Unit 9 review guide. So remember, before you watch this video, first try it yourself. Then check the written answer key. Finally, come watch this video at the end. This video should only be used as a last step once you've tried it on your own. So let's get started. Number 1, we're asking what feature of the longitudinal wave shows the stretched region. That is a rarefaction. D. So compressions are the compressed regions of high pressure, and rarefactions are the regions of low pressure. If two sound waves pass through the same medium and have different wavelengths, well, that means they have the same speed, same medium, same speed, but different wavelengths indicates that they must have different frequencies, because frequency and wavelength are inversely related. So I said C, difference in frequencies. They have the same medium, so it's not A. The same different amplitudes doesn't change the wavelength, so it's not B. And finally, they're both the same type of wave. They're longitudinal, that is pressure waves, and specifically the pressure wave of sound. For number 3, a 2-meter long rope is fixed at both ends. If I start calculating out the different wavelengths, let's say I do my first harmonic. I would do lambda is 2L over 1. So the first harmonic would have a wavelength of 2 times 2 over 1. The first wavelength is 4. Since it's which wavelength would not produce a standing wave, D is not an option. All right, so let's do the next one up. The next standing wave would have a wavelength of 2L over 2 or 2 meters. So it's not B, that's my N equals 2 wave. My third wavelength would be 2L over 3 or 4/3. That's not an option in either direction. And finally, my fourth wavelength is 2L over 4, so that's 2 times 2 divided by 4, or 1. So I found that 4 meters, 2 meters, and 1 meter all correspond to different possible wavelengths of standing waves by calculating this out repeatedly. The only one that didn't pop up was 3 meters, C. Sound waves are longitudinal waves. They're pressure waves of compression and rarefaction that travel through usually the air when you and I hear them. We haven't done electromagnetic waves yet. They absolutely do require a medium for transmission. I can't have high and low pressure regions without a medium to carry the pressure. And you can either be longitudinal or transverse. Sound waves are not transverse, ergo C, longitudinal. The region of a sound wave in which the density and pressure are greater than normal is called the compression. We actually went over that in number 1. The pitch depends on the frequency of the sound wave. Remember, the amplitude is kind of proportional to loudness. There's some other human things going on there where we can't hear certain things outside of the range of human hearing anyways, not power or speed. In general, sound waves travel faster through solids, then liquids, then gases. So I would say A, faster in solids than gases. The more density you have, the easier it is for one particle to hit another particle and transmit that wave. For number 8, a train moves down the track towards the observer. The sound from the train, as heard from the observer, is higher in pitch than the sound heard by a passenger on the train. So that is C. This is the Doppler effect, which occurs with all waves. D. Now let's address both of those together. As the train moves towards the observer, that crunches the wavelengths up in front of the train. There's my train and the little tiny wavelengths. Smaller wavelength means higher apparent frequency because the speed of the wave is the same. It's still sound, so 340 meters per second in air. And since the speed stays constant, that shortened, compressed wavelength causes an increase in frequency. The person who's the observer will hear a higher pitch or an increased frequency, whereas someone sitting on the train doesn't hear this. Those sound waves out in front of the train aren't traveling through the cabin in the same way. The person in the train has no relative motion, and no relative motion means no Doppler effect. The Doppler effect can be done with all waves. You see it as bow waves on the front of a ship. You can see it with light waves when we start talking about red and blue shift. So any wave can do the Doppler effect. Number 10 is a vocab question. When the frequency of a force applied to a system matches the natural frequency of vibration of the system, you get an increase in amplitude, and this is called resonance. Keywords to be looking for here. Resonance requires three things. It requires a system that can vibrate or oscillate. That's number one. Number two, it requires some sort of applied force. But you just don't push the object once. If you were pushing someone on a swing and you just hit them really hard one time, you wouldn't get resonance because the amplitude would decrease over time. However, if you continuously apply that force at the correct frequency, you get an increase in amplitude that we call resonance. Number 11 is an algebra question. Let's say we put in L and just leave it as a variable. The fundamental frequency has N in the denominator equals 1. 2L over 1 is just 2L. So 11 is C. Number 12. The quality of a musical tone of a certain instrument results from a combination of harmonics. When we've calculated out the harmonics for a piano string, for instance, we see there's peaks at different frequencies. Your fundamental frequency will have the largest amplitude, and its harmonics will be evenly spaced with usually decreasing amplitude. So for instance, if my first harmonic was 200 Hertz, I'd also hear in the background a complex combination of all my other harmonics. The 400, the 600, the 800, all the other harmonics would play at the same time, making a sound wave that sounds more complex. Musical instruments don't sound like function generators because they're made up of all these different harmonics. 13 and 14 both deal with this idea of interference. When you have two waves traveling through the same medium, they interfere with each other. And interference means that at any given point, the amplitudes of the waves add. So at point A has part of the wave being negative, part of the wave being positive. Those two amplitudes cancel each other out. So if this amplitude is -5, and that amplitude is +2.5, then I expect that these cause destructive interference. Destructive interference means that the amplitudes partially cancel each other out, making less amplitude of sound, so maybe a quieter sound or a dimmer light. At point D, on the other hand, both are negative. And let's see here. Blue has an amplitude of -2.5, and hey, so does red. When we add those two together, they have an increased amplitude. Now their amplitude is -5. That has two waves adding together to make a larger magnitude of amplitude. That is constructive interference for A. This year we didn't do beats, so it can't be those. And for harmonics, neither of these are talking about standing waves. Remember, harmonics are frequencies related to a standing wave in an instrument. A musical instrument can have harmonics, like a string instrument or a tube instrument. But just regular old waves, they don't have harmonics unless they become standing waves. Number 15, sonar technicians are working on active sonar. Remember, active sonar is when the buoy releases sound, waits to study the reflection, and can use the time of reflection and frequency of reflection to figure out how far away is your object and how fast is it moving towards or away from you. So they're designing this buoy, and the buoy releases a 600 hertz sound pulse. They find the wavelength is 0.57 meters in air, and we calculate the speed of sound. Fun fact, on this test, I will ask you to show your work. And what that means is, even if you write me down the correct answer, if I can't follow it or necessarily understand what you're doing, that might not be good. You might not get partial credit if you mess up. So here's how you get your partial credit. This says calculate, and calculate means write me an equation. Now, I know I'm calculating speed, and there's two potential equations. The definition of speed is distance over time, or wave speed is wavelength times frequency. What do I have enough information to solve for? The second one. So I'm showing my work. I'm writing down what equation I'm using to solve here. V is equal to lambda f, so lambda is 0.57. Frequency is 600 hertz. That puts my wave speed at 342 meters per second. That sounds about right. We've been using 340 meters per second, but maybe this is hot air, and in hot air, waves travel faster, or sound waves travel faster at least, than in cold air. Now, the buoy is placed underwater. When it goes underwater, the frequency remains the same. Remember, it's still releasing a 600 hertz sound pulse. The source is still vibrating back and forth with that really rapid frequency. And it's asking me to calculate the frequency and wavelength. But hey, fun fact, I know the frequency. It's still 600 hertz because this is the same source. Same source, same frequency. But what changes is it's vibrating a different medium, and that will change the speed of sound. Notice in this case, the speed of sound in the liquid is higher than in a gas. That's to be expected because, as we mentioned, the density of a liquid makes it easier to transmit from particle to particle to particle a sound wave through the water. So I want to find wavelength, and there's two equations for wavelength, so I'm going to write down both. There's lambda is 2L over n, or V equals lambda f. Lambda doesn't occur in any other equations. But I know it's not the first one because this is only true for standing waves. That doesn't apply for waves in general. So I'm going to be using the same equation again. I'm going to say V is equal to lambda f, where V is the speed of sound, is 1500 meters per second. The wavelength is unknown, so I'm going to leave that a lambda, but the frequency remains 600 hertz. Lambda equals 1500 over 600. That is 2.5 meters. So I want to point out that this is actually a really good example of refraction. If the sound wave started in the air and then started traveling through the water, the speed would change. Then the wavelength would change. So let me just put these side by side. The frequencies both stay 600, 600 in A, 600 in B, but in A, the wavelength is small because the speed is small. In B, the wavelength is larger because the speed is larger. Excellent, moving right along. Draw a line to represent the amplitude of each wave, mark it with an A. Notice you could do above or below equilibrium. Those would both be the same distance. Similarly, this could be an A, that could be an A. Those are both amplitudes. Then same thing for wavelength. I'm going to do crest to crest. I like that. Wavelength is crest to crest. But if you wanted to, you could draw trough to trough. You could draw equilibrium to equilibrium. As long as you choose corresponding parts on adjacent waves, like the corresponding crest to crest, then you're good. All right, so I'm going to draw trough on wave B. Ooh, just noticed a thing, and I will fix this on your copy when I get a chance. This should say amplitude versus distance. In order for this to represent wavelength, this needs to be a distance on the x-axis instead of a time. The longest period requires the smallest frequency, so perhaps it makes sense to answer D first. For D, I'm going to say something like both waves are traveling through the same medium. And since both waves have the same medium, that means they have the same speed. So if V stays the same, that means lambda and F are inversely related to each other. The one with the higher frequency must have the smaller wavelength. So A is an example of a wave with high frequency and a small wavelength. B must be the opposite then. B, notice the longer wavelength, must have a low, small frequency. That means for C, the wave with the longest period is actually going to be B. B has the longest period because B has the lower frequency. Since period is inversely related to frequency, B's lower frequency requires it to have a longer period. Low frequency implies long time period, and this high frequency of A means short time period. Think of it like this. If it's going very quickly, it doesn't take a lot of time to complete one cycle. "17 is on the Doppler effect again. B, here's the highest frequency. And that's because B has the car approaching them. As the car approaches them, look at all these crunched up little wavelengths here. As the car is approaching, wavelength is small for the same speed. And that means that it's going to hear a higher frequency. Oh, and then the reverse is true. A would hear the lowest frequency because notice how as the car leaves, goes away from person A, that causes the wavelength to stretch out. And since those wavelengths are longer, the frequency is smaller for the same speed. They're inversely related. So A here's a lower frequency than B. All right. So let us do some standing waves. First, we've got a guitar string with a wave speed of 624 meters per second. And the first harmonic is when my wave, my incident wave, travels down to the end of the string and reflects so that my incident and reflected wave interfere with each other in the same medium. This puts an antinode in the center and nodes on either end. The wavelength of this first harmonic, where it says show your work, remember, I could use one of two equations for wavelength, but only one makes sense in this context. I know the length of the string, and I know the first harmonic, also called the fundamental frequency. While I have V, I don't yet have F, so I can't use my wave speed equation. Substituting in 2, I'm going to change L into 0.6 meters. 2L over 1 is equal to 1.2 meters. I would get both points here. I get 1 point for my equation, 1 point for my answer. Now I want to calculate frequency. Now I can use this equation. Because I know the speed and wavelength, I can find frequency. Notice I'm not putting in V as the speed of sound. I'm putting the speed of the transverse wave on the string. 624 meters per second divided by 1.2 meters would give me my frequency. In this case, that would be 520 hertz. If I were to go farther with these, I would see my next frequencies. It would be 520, 1040, 1580, and so on. These would all have the same speed of 624 meters per second because same medium, same speed. But they have different wavelengths. The wavelength starts large at 1.2 meters and must get smaller because as we go up to the other harmonics, well, that's trying to fit more antinodes in the same length. So each antinode must get smaller in order for them to fit. So I drew my incident wave going towards the boundary, my reflected wave going backwards, interfering through the same medium. So I have antinodes, 3 antinodes, and then I have nodes. I actually calculated the frequency of my third harmonic in my head. What I had done there was I had done the frequency of the third harmonic is equal to 3 times the first harmonic. So let's do that out. This says show your work, so you get a point for the equation. Make sure you write that on your test. That's what show your work means. F3 is equal to 3 times the fundamental. Or in this case, 3 times 520. Oh, silly me, mathed wrong earlier. This would be 3 times 520 is 1560, not 1580. So silly. Now, here's the thing. If I want to find the third harmonic, I actually have 2 different ways I can do it. I can note that they have the same speed and divide across the row. Since this has to obey the wave equation across every row, that means I could find the wavelength by dividing 624 by 1560. That's one way. And if I wanted to show my work for that, I would do V equals lambda F. 624 equals lambda times 1560 and divide on both sides. This would get me lambda as 0.4 meters. Ooh, and if I've done this way, I can double check the other way. Alternatively, I can do lambda is equal to 2L over N. Since this is my third harmonic, that would be 2 times 0.6 over 3. And that gives me the same result, 0.4 meters. So I must have done something right if both ways find me the same answer. If the tension in a guitar string is increased, well, what that actually changes is a property of the medium. Listen to this. By increasing the wave speed in the medium, I increase the frequency. But what I don't change is the wavelength. The speed increases, so the frequency increases, but the wavelength depends on the length of the string. Remember, wavelength is 2L over N. Since wavelength is 2L over N, the wavelength of the first harmonic remains the same. It would still be 2 times 0.6 over 1, or 1.2 meters. But if I take the guitar string and shorten it by placing a finger on one of the frets, I'm no longer changing the medium. What I'm changing is the length of the string. So let's say my string is this long, and I put my finger somewhere else. It's the same medium. Same medium, same speed, but I have shortened the wavelength. I've shortened the wavelength because instead of 0.6 meters, maybe I put my hand farther up. When I put my hand farther up, L decreases, so wavelength decreases, and that means if wavelength decreases for the same speed, same medium, that must mean the frequency increases, which we could even hear before. Which brings us to the last page, a lab setup that has a speaker connected to a function generator. The speaker is set next to one end of a tube that's opened on each end. The first standing wave, label nodes and antinodes. I need to draw one complete antinode, but still keep a half on each side. This is the first harmonic, because imagine this is half of an antinode plus half of an antinode makes one complete antinode. First harmonic. In this case, this is what is the wavelength. This should really be calculate the wavelength of the first harmonic and show your work. That's what I want you to do. So calculate the wavelength of the first harmonic. Let's give you some equations here. Show our work. That's 2L over 1, or in this case, that's 0.68 meters. The first resonance frequency heard is 520 hertz. What we would do is we would scroll up on the function generator. slowly increase this frequency until we hear the loudest amplitude sound. That would be resonance. Remember, resonance, you play in the correct frequency. That causes an increase in amplitude. So my first resonance frequency is the same thing as the fundamental frequency or first harmonic. If we know the wavelength and frequency, we can calculate the speed of sound in air and show our work. So I'm going to do V equals lambda F. Lambda is 0.68. Frequency is 520. And so our speed of sound in air is 353.6 meters per second. Now, that's a little bit high. That could be because the room is a little bit warmer than it should be. If the room is warmer or more humid, or even has a lighter gas mixture, let's say someone popped a helium balloon in the room, that could increase the speed of sound because lighter particles are easier to move than heavy particles. And hotter particles are moving faster, so that's easier to transmit sound from one particle to the next. Okay, so next, we continue scrolling up on the frequency. Calculate the second frequency where resonance occurs. Okay, well, if I know the first frequency is 520 hertz, well, that means the second frequency is 2 times larger than it. The second frequency would be 2 times 520, or 1040 hertz. That note would be 1 octave up. The second harmonic needs to have 2 complete antinodes, but still keep antinodes in each end. All right, so how do we do this? I'm going to put half an antinode in each end and a whole one in the middle. Notice, this is half plus a whole. This makes 2 complete antinodes. There are 2 nodes in this picture. There's 1 node in this picture up there. Great. And if you have trouble remembering them, student-made nicknames. Remember, this is the bow tie and the hard candy. It's got those little ends of wrappers over here. Calculating the wavelength through the second harmonic. You get 1 point for the equation and 1 point for your answer. So even if you mess this up somehow, you get a point for writing the wavelength equation. Do it. 2L divided by N. L is 0.34 meters. N is 2. And that's math even Miss Pasega can do in her head. That is 0.34 meters. So let us do out a harmonic table, right? So we started with frequencies that we knew, right? We had 520. 520 times 2 is 1040. 520 times 3 is 1560. 520 times 4 is, 2080. 520 times 10 is 5,200. Now let's do wavelengths. The wavelengths are going to be your 2L over N, but we've already done the first 2. So we had 0.68, 0.34. Next up, let's do 2 times 0.34 over 3. L is the length of the entire tube in meters. That gives 0.227, or just about. I'm rounding it to keep all the same significant figures. No big deal either way. So how about 2L over 4 now? That's 2 times 0.34 over 4, or 0.17 meters. That means for the 10th harmonic, that's 2L over 10. 2 times 0.34 over 10 is equal to 0.68 over 10, or 0.07. Just about 0.068 meters. Notice the wavelengths are getting smaller because we're fitting more waves in the same tube. And the frequencies are getting larger. Actually, if you mathed this out, you could actually calculate the speed of sound at all these different frequencies. Use that to calculate the average speed of sound for all your trials. Ta-da! You've reached the end of the video. At this point, things you can do to help yourself. You still get open notes, and none of my other students in previous years could have done this. You still get open notes. Use the back page of this sheet, of this review packet, to make sure you've got all the equations you think you need. You could even do things where you write out examples. How do we use the time period equation, the wave equation, the harmonic frequency equation? If you see vocab words that you don't think you know, you could go look them up and write them on your note sheet. All right, so best of luck, everyone. See you next time. Bye.